Hello, my dear students. Welcome back. Today, we're going to look at a chapter that I know can feel a little bit tricky, electrochemistry. But please, don't worry at all. We are going to make it super, super simple for your exams. I know, exams are just around the corner and the pressure is building up, but trust your teacher, okay? After this quick session, you're going to feel so much more confident about electrochemistry. So come on, let's do this together. So, first things first, what is this big word electrochemistry? Well, think of it as a story, a fascinating story about the connection between chemical reactions and good old electricity. Let's see how they are related. Really, it's all about two main ideas. Number one, how we can get electricity from a chemical reaction, and number two, how we can use electricity to make a chemical reaction happen. Your phone is the perfect example. When you're using it, a chemical reaction is making electricity, and when you charge it, you're using electricity to reverse that reaction. See? Electrochemistry is everywhere. Now, we all know that electricity flows through wires, right? But in this chapter, we are talking about solutions, about liquids. So how on earth does electricity travel through something like, say, salt water? Let's find out. Okay, imagine this. Resistance, which we call R, is like a big traffic jam that slows down the current. It's an obstacle. But conductance, or G, is the complete opposite. It's like a wide open highway where the current can just zoom past. In fact, G is just 1 divided by R. Simple enough, right? Now, don't get confused between resistance and resistivity. Think of it like this. Resistivity is a natural property of a material, kind of like its color or density. Some materials are just naturally better at resisting current. And conductivity? Well, that's just the opposite. It's how good a material is at letting current flow.
All right, bachcho, eyes on the screen. This table is a perfect summary of all these terms, their symbols, and their units. I would really suggest you take a quick screenshot of this. It's going to be a lifesaver for solving numericals and those 1-mark questions. Exam alert!
Next up is a very important concept, molar conductivity. I know, the name sounds a bit heavy, but the idea is actually very simple. It's just a way to measure how well a solution conducts electricity when you dissolve exactly 1 mole of a substance in it. That's it. It just helps us compare different substances fairly. So, knowing the theory is great, but applying it is what will get you the marks. So let's solve a typical problem, okay? This one is straight from your textbook, so it's super important. Get a pen and paper, let's do it together. We can do this in 3 easy-peasy steps. First, we find the resistivity using the formula R times A divided by L. Got it? Second, we find the conductivity, which is just the inverse of resistivity. So 1 divided by resistivity. And finally, we use this formula right here to get our molar conductivity. Just follow these steps and you'll solve these problems every single time. Okay, now let's talk about something that is a real game changer in this chapter, Kohlrausch's law. This is a very, very, very important topic, so I need your full attention for just a minute. The official definition sounds complicated, doesn't it? But the idea is actually quite straightforward. It just says that when a solution is super dilute, each ion, the cation and the anion, moves around freely and contributes its own fixed value to the total conductivity. It's like they're all individual players on a team. So, what's the big deal about this law? Why is it so special? Well, it's a very clever trick. You see, for weak electrolytes like acetic acid, it's almost impossible to measure their molar conductivity directly. This law gives us a brilliant, indirect way to calculate it. And here is how the magic works. To find the conductivity for acetic acid, we need the values for the H+ and acetate ions. So what do? We take 3 strong electrolytes, HCl, sodium acetate, and NaCl. We simply add the values for the first 2 and subtract the value for the third one. The unwanted ions just cancel out, and voila, we are left with the exact value we wanted. It's just simple addition and subtraction. Okay, enough with the theory and formulas for a bit. Let's see how all this stuff actually applies to the world around us. Let's talk about batteries and fuel cells. This is very simple. Primary cells are what we call use and throw. Think of the battery in your TV remote. The chemical reaction only happens once. When it's over, the battery is dead. But secondary cells are rechargeable. The chemical reaction can be reversed. That's why you can plug in your mobile phone and charge it again and again. Here's the classic dry cell, the kind you find in wall clocks and radios. For your exam, just remember this. The outer zinc container is the anode, which is negative, and the carbon rod in the middle is the cathode, which is positive. That's the most important part to remember. And now, let's look at the future, the fuel cell. This one is amazing. It uses hydrogen and oxygen to make electricity, and the only thing it produces is water. So it's super clean and efficient. And here's a fun fact. This technology was used in the Apollo space missions to give astronauts power and drinking water. How cool is that? And finally, let's talk about a not-so-great but very important electrochemical process, corrosion. You all know it as rusting. It's a natural process, but one that causes a lot of problems. I'm sure you've seen this everywhere. The brown-red rust on an iron gate, the blackish layer on silver jewelry, or that green coating on copper vessels. All of these are examples of corrosion. It's just a metal slowly getting destroyed by reacting with its environment. Now, the reason we study this is because corrosion is a huge, huge economic problem. In our country, India, the damage caused by rusting to bridges, ships, cars, and buildings costs us crores and crores of rupees every single year. It's a silent enemy that costs us a fortune. All right, let's do a super quick revision. So, electrochemistry links chemical and electrical energy. We learned how to calculate conductivity. We saw how Kohlrausch's law is a neat trick for weak electrolytes. We looked at real-world examples like batteries and fuel cells. And finally, we understood that corrosion is a very expensive problem. Before we end, I want to leave you with one question to think about. Your textbook talks about something called the hydrogen economy. So based on what we learned about fuel cells today, how do you think we can use these ideas to create a cleaner and greener future for our country, for India? It's something important for all of us to think about. You have all done a fantastic job today, my dear students. I'm very proud of you. You are now absolutely ready to face this chapter. Go into your exam hall with full confidence and just do your best. My blessings are always with you. All the very best.